Okay. Oh.
So our next speaker is Aihua, and she'll talk about restricted edge connectivity of alternating group graphs.
Thank you. I'm going to follow the pattern of the last two talks, bringing algebra to graph theory. So my talk has a group theory. All right, so I'll talk about some graph built by the alternative group. Thank you for the organizer also for giving me the chance. So I'm going to give a little history and background on the alternative group graphs built from the group of all even permutations. That's A sub n. Okay, and then the second one, restricted edge cut and restricted edge connectivity. That's defined for all general graphs. Doesn't have to be the alternative group graphs, but my focus will be on this alternative group graphs, and that is denoted by AGN. Okay, and there are some main results I'll bring up and some open questions at the end. So this one has a lot of application in computer science. Actually, it was start with one I collaborated with some visitors from China. One of them is in the computer science, and she worked on the networking things. So this type of this class of graphs is actually Cayley graph of the alternative group. If you recall, the Cayley graph is when you have a group, you can take the group members at the vertices, and two vertices has one edge if but you fix a number from the group is A times G equal to B, then you have an edge from A to B. So that's kind of a Cayley graph. It has both directed or undirected graphs from a group. But this one actually provide a very natural and rich framework for the design and analysis of interconnection networks for parallel computers. They actually have the vertices to be the processors. And then the links, of course, they should have some interconnection between the processors. And in computer science, they have this popular kind of this type of network. One of them is called a hypercube, especially the binary hypercube, and orthogonal graphs and star graphs. We all know star graphs, and that belongs to this type of networks. And also, this interconnection networks play an important role in the parallel distributed computer system, as I mentioned with the processors. Usually they use this to multiply a graph in which the vertices corresponding to the processors and the edges corresponding to the links between the processors. That's why the computer science people, especially theoretical computer scientists, they do research in this area. And in 1993, these two researchers first proposed this alternative group graph as a topology of interconnection network for multiprocessor systems. All right, so here are some basics about the alternative group, A sub n. This is the group of all even permutations. You know that S sub n has n factorial elements. This has exactly half of them. And actually, the alternative group can be generated by only 3 cycles. 3 cycles are even permutations because you can write that into a part of two cycles. And for I, this index greater than or equal to 3, this permutation 1 to 2, 2 to I to 1, or 1 to I to 2, 2 to 1, these are the two type of 3 cycles that generate the whole A sub n. Actually, just using the first type is enough. You can, if you do the square of the 1 to I, you get 1 I2. So that will be automatically in the group. But here, in particular, we have this AN is generated by the 3 cycles in this form, 1 to I, where I is greater than or equal to 3. So now we define our alternative group graph. AGN, the vertices of this graph is the set the members of the alternative group A sub n. So just take all the even permutations as the vertices. And for two vertices in this or two members in this alternative group, we have an edge in between if and only if so for alpha and beta. Beta can be obtained by alpha multiplied by 1 to I for some I greater than or equal to 3, or the other one, beta is equal to I alpha times 1I2. And you can show all of the these relationships to give you the address of the graph. I'm going to show you example graphs, but we're going to take these two types, kind of two functions. One is gi plus, the other is gi minus. It's just based by multiplying from right those two cycles. And I mentioned before that the square of 1 to I is 1I2. So here is our definition for the alternative group graph. Okay, and actually you can look at the generating set. These two type of 3 cycles, 1 to I or 1I2, we can generate the whole alternative group. So that's the order of the group, the graph also. Okay, generating this is only the generating size is not the smallest. That is our graph. So let's look at the graph. I have the graph here. This is one for AG3, the other for NG4. Okay, NG3, if you look at, but they use the kind of a different notation, like for A3 has only 3 members, the identity and the 3 cycle 1, 2, 3, and 1, 3, 2. Square of 1, 2, 3 is 1, 3, 2. But when they made the graph, the people use this notation. They use this like 1, 2, 3, 2, 2, 3, 1. They use this row as the symbol. So that is that 1, 2, 3 is not the identity permutation. That 1, 2, 3 means 1 goes to 1, 2 goes it is identity for that one, but if you look at this one, 2, 3, 1, that means 1 goes to 2, 2 goes to 3, 3 goes to 1. It's not the cycle 2, 3, 1. Okay, it's a little confusing at the beginning, but if you make the connect using this notation, just the second row is the symbol there. So 1, 2, 3 is the identity of the 1 to 1 go 2 to 2, 3 to 3. And E times the 1, 2, 3, you get a 2, 3, 1. Okay, 2, 3, 1, that actually is the cycle notation of this one. 1, 2, 2, 2, 2, 3, 3, 2, 1. And the other one is multiplied by 1, 2, 3. Also, you get that 1, 3, 2 using or 3, 1, 2 using that notation. So there are 2 notations. So this build a 3 cycle triangle. That's for A3. And for A4, let's just look at the 2 vertices there. The top one is 4, 1, 3, 2. That means 1 is set to 4, 2 is set to 1, 3, 2, 3, 4, 2, 2. That is 4, 1, 3, 2. If you multiply one of the generators, 1, 2, let's do 2, 3, 4. If we multiply by 2, 3, 4. This one actually, if you write the cycle notation, is 1, 1, 2, 3. With that notation, but multiply by 1, 1, 2, 3. You can multiply 1, 2, 3 from that edge, and it is 2, 3, 4. Or using the other notation that is 1, 3, 4. That's straight going down. Okay, so that's the connection between 4, 1, 3, 2 to 1, 3, 4, 2, and all of the edges are built in this way. This is the graph for the first two, AG3 and AG4. Okay, now for this graph, just to quickly mention some properties. This graph is considered as the topology of the interconnection network for multi-process systems I mentioned before. People were thinking about this graph is good because it possesses sufficient amount of good properties, including the cycle embedding and small diameter. And also, this is not only pancyclic and Hamiltonian connected, but also pan-connected. Pan-cyclic is like this graph has all cycles of length from 3 to the maximum number of the group, the graph. Okay, and AGN also has a fault-free longest path and the vortex pan-cyclicity. I kind of now I don't recall what is the fault-free, but that's useful when they do the processor thing. And now one property probably I want to put here is noticeable and also is useful to prove the following later theorems. And also from the point of a graph theory, maybe this is an important property. If you take any two vertices from the graph, the intersection of the neighbors of them, the size is only 1 or 2, less than or equal to 1 or 2. So less than or equal to 2, basically. If UV make an edge in the graph, then they only intersect at most one vertex, the two neighbors. And if the UV is not an edge, then it's intersect with at most 2. Maybe that's a good property when anything we need to consider the neighbors. I want to go back to the graph. If you look at this graph, see just the this edge from 4132 to 3412. You can look at the neighbors of the two endpoints, and that's one edge. Okay, there's only one intersection, 1342, in the intersection of the two neighbors. And if you look at the two vertices without edge in between, like 1342 and 2314, you can look at their neighbors, and they don't have many intersections, right? So based on the result is at most 2 vertices in the intersection of the two neighbors. Okay, that is a nice property in some sense. That is the about a property of the this alternative group graph. So here we make this definition for the restricted edge connectivity. It doesn't have to be for the AGN. You take a subset of edge set. S is a set of edges, and M would be a positive integer. Then we say S is restricted edge cut or order of order M if you take away this S, this set of edges, the graph is changed from connected to disconnected. Okay, so if S is just one edge, you get a bridge, right? Cut one edge, then you get disconnected, and this is called the restricted edge cut, the M restricted edge cut, and using this connectivity, the notation lambda M of G, this is called the M restricted edge connectivity of the graph G. That is the minimum size of all of the edge set. Okay, that S is an order M restricted edge cut of G. Okay, we also have the one thing I didn't emphasize. We also need after you cut this S, this set of edges, the graph becomes disconnected, but each component consists at least M vertices. So you take away some edges, like you get a 2 component, each of them has at least M vertices. Okay, that is the main thing for M restricted edge connectivity. Okay, and the original edge connectivity lambda is actually the lambda 1, right? As you edge connectivity, right? So if M equal to 1, then at least you have 2 disconnected, more than 2 or 2, at least one vertex in each component, right? So that is actually lambda 1 is the ordinary edge connectivity of the graph G. But now we have lambda 2, lambda 3, and so on. So here, if you look at this as to be the set of the right edges right here, if you cut this from here, you see the 2 disconnected set, each of them has 4 vertices. So this is a 4 restricted edge cut. And also, no matter how you cut, get the number for G is actually 4. Okay, that is the definition. So also to get those numbers, this is a well-related number with the lambda m. So we take a subset of vertices, F. You take a F and then take the rest. So G taking away F, and then this partial F is all the vertices in F bar, which are adjacent to at least the one vertex in F. So if my F is this right dots here, 4 vertices here, and you look at F bar is those white vertices, and we want to know the partial set is all the vertices which is connected adjacent with at least one of the vertices in this F. So all 4 of them. Okay. So in this way, the partial F is 4. I have all of those 4 vertices there. Okay. F is the right, and this partial F is all the rest. And this perceived 4 of G is the minimum of the partials of F. You fix this F, you take all the others, and go over all of the F with size M. Okay, this is another invariant, and it's related to lambda M of G. Okay, so these are the main definition. Now, for an existing result, actually there are a lot of paper worked on the restricted vertex connectivity instead of edge connectivity. That means you take away some vertices, then each disconnected component has at least M vertices. And not many paper on the edge, restricted edge connectivity. There are some papers, it's mostly about giving a bound for this numbers of M. But here, if we look at this, the graph first, AGN, some properties about AGN. AGN is 2n minus 4 regular, so it's a regular graph. And the connectivity chi of AGN is the minimal degree, 2n minus 4. Diameter of the graph is 3n minus 6 over 2. And all the cycles of length with, so you can find all of the cycles of length starting from 3 to the size, the order of the graph. Okay, so that's called the pancyclic. Okay, and also for large enough n, this restricted the lambda is always less than. Actually, this one works for a lot of other m's, okay, with some conditions. Okay, and this is the about some properties about this graph. Ooh, what happened to this? Okay, so there are results about this AGN minus vertex cut. Okay, and then for some sets, there are several results on this, not only this condition. I pick this is the most general one. If the vertex set is small enough, less than or equal to 6n minus 20, so you n should the n factorial over 2 is kind of big, and this graph will satisfy one of the following. So the you take away this vertex set, and will result in 2 connected components. One of them is a singleton. So when you try to find the lambda m that this is needed, what type of component we have, and the other case is has 3 connected spelling. Has 3 connected components, 2 of them are singletons. So there are also a set of other conditions similar like this. So after you cut off this vertex cut, what the component types you will get, and there's also a boundary for the edge for the size of any induced subgraph of AGN. You take a induced subgraph H. And this inequality actually equality holds for n equal to 6 and 7. If you plug in, you get 8 and 10, and we can actually prove that is true. But I picked this one to give a little proof, and instead of the other thing I'm not going to talk about, the proofs is quite complicated. This one I will give a better bound for the minimum degree. If you take a subset, induced subset H, then the minimum degree of H is less than or equal to T plus 2 over C, where T is the order of the graph H. Okay, and it's actually using the previous properties. When you take the minimum degree is, let's say, is R, the minimum degree is R, and you take a vertex with degree R, so I have R vertices adjacent to U, and then based on the previous property, the neighbors of V1 and V2, we can add there if it has edge in between, they intersect at most one vertex. The other case, if the V1 and V2 has no, I forgot to erase one of the edges. I copied the paste and paste. If V1 and V2 is not an edge, remove that V1, V2, then the intersection is at most 2 of the 2 neighbors. So either case, you're going to just add all the rest of the angle, the vertices, and there is the minimum degree is R, so there's greater than equal to R. Okay, so just do a little calculation, we can get this bound. And then from this is the main thing for the proof of the main results. We only get some small numbers, getting very messy. So we get this lambda 3 is 6n minus 18, which is the same as the 63. And so we first look at that kind of look at the value there, then prove they are equal. And we get a lambda 4, lambda 5. And for the first one, lambda 1 is the ordinary edge connectivity. And lambda 2 is when you have the disconnected component, each has at most 2 vertices. Those are easier to prove. So this is the main result for lambda 3, 4, 5. And we also get C is better. We get the 6, 7, 8, but we cannot prove they are equal to the lambdas. But we know they are, a lambda m is less than or equal to Cm, but we cannot prove they are equal to. So it remains this question. And actually we see good pattern here, at least for the, well, even this one or that one, we see the first part is 2m. M is the M restricted that M, okay? But the minus at the beginning has good pattern and later is something mess up. But so the question, can we use mass induction or some other method to prove this, to get a formula for the lumps of M, or try to show if they are equal or getting a bound, whatever. So there are questions to answer. I'm thinking about to let my master student of mine to do the work on for m equal to 6, lambda 6. Start with the next some small number. We got a PC6, but we haven't got if they are equal or not. And that is my talk. Here is the reference. And thank you for your attention. Questions?
Can you go back to the last slide? No, I mean the one before. So
Yeah,
18
those.
plus 6, 24, 24 plus 8, 32.
Yeah, but then the next one is 40, but it may not be that one because this is only C6. So
I'm talking about the lambdas.
yeah, so the lambda, the next one, if you look at the at 6, at 8, the next one of 6 at 10 will be 42. I don't know.
Which is
But here is this because it's that we don't mean they have to be equal. Yeah.
it's okay, it's less, right?
But
Lambda is less than C.
yeah, yeah.
So it's possible. Do one more.
Yeah. Right. It has many cases. It's messy, the proof that Islam, so I'm not picking those proofs. Yeah. But yeah.
The few showed they were like polytopes. but
Yeah,
Are they all? So do you end up with crossing?
actually, I don't have the larger size of the graph. But I don't know. Probably yes. But it will be a lot of points. If you look at AG5, that will be 60 vertices. So,
Dimension would,
uh,
the dimension would be in the dimensions.
yeah,
Might be hard.
I don't know.
Yeah, like a sequence of vertices or anything. I guess that's going up by the AF.
Mm-hmm.
I was just going to call it.
Yeah. Yeah.
Only 1 minute? Yeah.
I can take one on your laptop, right?
Yeah,
Take it.
I think.
Diseases in the same way that